All right, let's talk about something that's happening inside your computer right now, something absolutely critical but that most people never think about. I'm talking about input/output, or I/O. Seriously, without it, your super powerful computer is just a box of sand, completely silent and cut off from the world. I/O is how it actually does anything useful. So here's our game plan for this explainer. We're going to start with the big problem, what we call the I/O bottleneck. Then we'll walk through the three big solutions that engineers came up with to fix it: programmed I/O, interrupts, and direct memory access. And then we'll see how it all comes together in this beautiful symphony of technology. Okay, so let's get right to the core problem. Picture this. You've got a CPU that's an absolute beast, a powerhouse that can do billions of things a second. But now it needs to talk to your keyboard or maybe send something to your printer. It's kind of like having a Formula One race car stuck in rush hour traffic. All that power, and it's just forced to crawl along. And I'm not kidding. The difference in speed is just staggering. Your CPU lives in the world of nanoseconds, which are billionths of a second. But your printer, your hard drive, they're dealing with physical moving parts. They're slow. This massive mismatch in speed is exactly what we call the I/O bottleneck. And what's really wild is the sheer range of speeds the system has to juggle. I mean, look at this. On one end, you have your keyboard, which is just this slow little trickle of data, one character at a time. But on the other end, you've got a graphics display that's demanding an absolute fire hose of data to keep your screen updated. And somehow, the I/O system has to manage all of this at once. So let's look at the very first idea for how to solve this. It's the simplest, most straightforward approach, and it's called programmed I/O. You can think of this as making the CPU the ultimate micromanager. It's in charge of every single detail. With programmed I/O, if you want to move a chunk of data, the CPU has to execute a command for every single piece of it. It's like a world-class chef who, instead of just having ingredients brought to them, has to personally run to the pantry, grab one single peppercorn, run back, and then do that for every single thing they need. It's simple to understand, sure, but man, is it a waste of the chef's talent. And this whole process just totally hogs the CPU. It issues a command, it waits for the slow device, it moves one tiny piece of data, and then it has to do it all over again. The entire time, all that incredible processing power is just sitting there twiddling its thumbs, waiting. So here's the bottom line. This method just doesn't work for anything fast. It's fine for, say, reading a key press. The data rate is super slow, and you actually want the CPU's immediate attention. But for moving big chunks of data, like from a hard drive, no way. It's a total non-starter. So, how do we get the CPU out of this waiting game? Well, the next big leap forward in thinking is the interrupt. Instead of having the CPU constantly pull a device, asking, "Are you done yet? Are you done yet? How about now?" the device can just tap the CPU on the shoulder when it actually needs attention. An interrupt is really just a signal that says, "Hey, CPU, drop what you're doing for a second. I've got something for you." This is huge because it lets the CPU go off and do other useful work, and it only has to deal with the I/O device at the exact moment its help is needed. And this process is just so elegant. Check it out. The CPU's humming along, running some program. An interrupt comes in. The CPU carefully bookmarks its place. We call this saving the context, so it knows exactly where it left off. Then it jumps over to a special little program to handle the request. Once it's done, it just pulls up that bookmark and continues right where it was, as if nothing ever happened. You know, interrupts are basically the secret ingredient in all modern computing. They handle your mouse clicks, they tell the system when a download is finished, the operating system uses them to juggle all the different apps you have open, they even handle major system errors. They are the nervous system of the computer. Okay, so interrupts are a massive improvement, but the CPU is still doing the heavy lifting of moving the data itself. For really big transfers, like loading a game level or streaming a 4K video, we need something even smarter. And this is where we get to the real masterstroke, direct memory access, or DMA. This slide really says it all. Without DMA, every single byte of data has to take this little two-step trip from the device into the CPU, and then from the CPU out to memory. With DMA, we just cut out the middleman entirely. The data flows directly from the device straight into memory. The CPU is completely bypassed. Let's go back to our chef. DMA is like the chef putting in a bulk order for 100 pounds of potatoes. A special kitchen assistant, that's our DMA controller, handles the entire delivery, bringing the potatoes straight from the truck into the pantry. The chef doesn't get involved at all until the assistant says, hey, all your potatoes are here and ready to go. And the process is just beautiful. The CPU's only job is to kick things off. It just tells the special little controller what it wants, where to get it, and where to put it. Then the CPU is totally free to go do something else while this huge transfer is happening. And how does it know when it's all done? You guessed it, the controller sends an interrupt to the CPU saying job's finished. This is why you can load a massive file and not have your entire computer freeze up.
So we've got these three powerful tools in our toolbox: programmed I/O, interrupts, and DMA. And the thing is, they don't replace each other. They all work together. Let's see how this whole orchestra comes together to make music.
And the star of this final piece is the I/O controller. This is a dedicated piece of hardware. Your graphics card has one, your disk drive has one, and its job is to be the conductor of this whole I/O orchestra. It's the real brains of the operation.
And just look at everything it does. It takes its orders from the CPU using simple programmed I/O. It manages those huge data transfers using DMA. And it reports back to the CPU using interrupts. It's using all three techniques we just talked about. Plus, it handles all the messy, low-level details of the specific device so the main CPU never has to.
And that right there is the teamwork that makes it all happen. It's this perfect three-part harmony. You've got programmed I/O for giving the orders, DMA for moving all the data, and interrupts for all the communication. It all works together, led by that I/O controller.
So from that simple, slow, one byte at a time method to this super efficient system, we've come a really long way. But the demand for data never, ever stops. When you think about massive AI models, fully immersive VR, 8K streaming, the I/O bottleneck is still the thing we're always fighting against. So the big question is, what comes next? Thanks for diving into this with me.